My name is Anna Shleiva. I'm a team lead for JEDI Data Simulation Algorithms team, and I'm going to start a series of 2 lectures on details of how the abstract layer in the object-oriented prediction system, OOPS, is working. I'll talk about the interface classes and a little bit about how those connect to DA algorithms. And then in the next lecture, Yannick Termele will talk more about the DA algorithms available in JEDI and some design ideas behind those. So I'd like to start with a recap of the main motivations and objectives of JEDI. We want to develop a unified data simulation system that can work with multiple models ranging from simple toy models to pretty sophisticated Earth system coupled models. So we want to have a system that would allow you to use the same data simulation algorithm, the same code for DA algorithm with different models. Another big objective is having a bank of unified forward operators, UFOs, something that you've heard about yesterday. So that would allow us to do this plug and play approach of picking the forward operators, the models, and the data simulation algorithms. We want to use this system for research and operation, and we'd like to share as much development as possible without imposing one approach. So if someone adds a DA algorithm, that benefits everybody. If somebody adds a unified forward operator, that also benefits everybody. Different models, different centers, or people who would like to use the system. And the idea is that you could, with using this one system, you can have both multiple configurations of DA algorithm, observations you use, observation operators you use, and the models you use. And also all of those are configurable, so you can also choose different configurations of those. So let's go back to the schematic that you've seen a few times already. So this block with all of the blocks here show parts of the OOPS system, object-oriented prediction system. It's the repository that you probably have noticed in the code when you were pre-using the code for the tutorials. So in this abstract OOPS layer, we have the top layer here, the darker blocks are generic algorithms or applications, as we call them. And examples here are HFX, something that you've run in the tutorial. So that's just computing HFX for specified observation in a specified window with the states from the model. We do have variational DA. There's ensemble of data simulations or EDA application and ENKF, and there could be, and there are others applications. And these applications are written inside OOPS in this sort of generic way by using the key component of the system, which is the blocks below those, which we call abstract interfaces here. So what those abstract interfaces are, they're basically these building blocks that allow you to write data simulation algorithms using those. And examples here are, some of them are related to the model. For example, state, which is a model state. I will talk a bit more about it in the next few slides. The model, the covariance, background error covariance in this case. Some others, the ops operator and the ops space are a few interfaces that you've already heard about in the previous lectures. And as mentioned before, this part of the system is kind of this abstract layer that doesn't make any assumptions about the nature of the state or model, or how the observation operators work, or how the ops space stores the data. So since this is pretty abstract, to be able to actually run a concrete variational data simulation with a model and some observation operators, we need to have implementations of these interfaces. So a few implementations here. Here I'm showing the generic implementations, or rather the repositories where you can find generic implementations of some of the interfaces. So all the interfaces that are related to things in the observation space are implemented inside two repositories. One is JEDI interface for observation data access that you've heard about on Monday. And the other one is the Unified Forward Operator UFO, which holds observation operators, QC filters, observation error covariances, etc. So the idea here is that by having this two generic implementation, or two repositories with generic implementation of observation related stuff, we are allowing different models use those implementations and not re-implement observation operators for each of the model. So this is part of this sort of generic layer below OOPS that can be shared by different models. Another another repository that you may have noticed inside the bundles that you've been using is called SABRE, stands for System Agnostic Background Error Representation. And that's where we have generic implementations of the background error covariances. So again, they are written in a way that allows them to be used with different models. So this is another example of something that does not have to be implemented for a specific model. So then, of course, there are things that have to be, that are model specific and have to be implemented for specific models. So an example here, we're saying that we also have an FA3 JEDI interface, which implements blocks like state, model state, and the model itself, or the model class in OOPS, which is slightly different than the model itself, and perhaps some other classes. Besides FA3 implementation, we can also have other implementations of model interfaces like state model, etc. We have a MOM6 interface developed by SOCA team, the Ocean Model interface, a Neptune interface, and multiple others that have been mentioned before. And the idea here is that, let's say we have this variational DA algorithm or application written in OOPS using this abstract interfaces like state and covariance, etc. We could then instantiate this application with implementations of observation operators from UFO and observation space from JEDI, covariances from SABRE, and let's say model-related classes interfaces from FA3. And we could run that application. Then we could do the same thing. We could use, without changing anything in the code of the generic algorithm or in the code of this generic layer, SABRE, UFO, JEDI, we could connect MOM6 interface, which implements state model, etc., to VAR-DA and to this generic layer and run variational assimilation with the observation operators from UFO for MOM6. We can do the same for all the other interfaces. So the key here is the separation of concerns between those three parts, if you wish. The one separation of concerns happens between the OOPS layer, so data simulation algorithms, and the underlying model and physical system. So the DA algorithms are written independently of how the model is implemented. The other part of the separation of concerns is that the implementation, so that let's say the FE3 or MOM6 implementation of the state interface doesn't know about the high-level algorithm. So state, model, etc., are implemented and could be used for any of the algorithms in OOPS, which means that everything, the interfaces should be pretty clear about what's passed, and everything should be passed through the arguments. And the key in choosing those interfaces was to be general enough to cater to all cases, but also detailed enough to be able to perform the required actions. And just to illustrate again this separation of concerns idea. So when we write the generic algorithms, basically, this is the view that we have. Write a new algorithm. We know this abstract interfaces, which is basically a concept, let's say, of a state and a set of operations or methods, what you can do with a state. So the interface defines the operations that can be done with the object of this class. And at this algorithms layer, we're calling the methods or the operations on those classes to achieve the goal of VARD in this case. And we do this without knowing how those operations are implemented, and we don't have to care about that. So this is what happens if you write a DA algorithm. On the other hand, if you're working on something like an implementation of the interface, let's say of an ops operator in UFO or a state for FE3 model or things like that, this can be done completely independently of the data simulation algorithms. So again, there's a defined set of operations that can be done on the state, and all the interface has to do is implement how that operation has to be done. And the key here is this layer of abstract interfaces and having them well-defined, well-documented, and clear what those interfaces are and what the operations are. So just I'll show you a few examples of those interfaces or interface classes. And we'll talk a bit about what operations, some of the operations that are allowed on them. But I'd like to start with kind of talking a bit about how those interfaces were chosen. So if you read the papers or data simulation papers or data simulation code, all DA methods require pretty much the same limited number of entities. And these entities could be or should be easily reusable for future developments. And those entities are those basic abstract classes or the interface classes that define the system. So to illustrate this, I thought it would be good to look at a few equations that are commonly used in DA and just show which of the entities in those equations are which classes or abstract interfaces in OOPS. So what is DA? We are aiming at finding the best estimate or analysis of the state of a system, given the previous estimate of the state or the background and the recent observations. And if we're doing Gaussian DA, we could use variational assimilation and minimize some sort of cost function. This is just one example of how it could look like. Or we could use a Kalman filter and compute the update using this equation. So the first interface class that we've already mentioned before that I'd like to talk about is called state. And state is basically a state in the model space. So If you look at highlighted examples here, it could be the background state, or it could be an analysis state, could be some forecast state from the model, or it could be an ensemble member if you're doing ensemble data simulation. So that's basically a vector in the model space. And the key in defining the interface is saying what operations are allowed or we can do with the state. So a few examples here. If we think about state and what we should be able to do with the state to do some valuable data simulation, we should be able to input it from file or from disk and output it. So like read in the background and output the analysis. This is the next operation is something that's not really defined in the state interface, but we should be able to propagate state forward in time using the model. So go from state at time 0 to state at time 1 by using the model operator. We should be able to copy and assign states, and there are a few other operations that are in the state interface, but I'm not going to talk about that right now. And from DA point of view, so if you're working on the data simulation, again, there's no need to know how the state is stored in memory or how the input-output is done. From the DA point of view, you're doing something similar to this or this. And the details of how to do I/O or how to assign a state or how it's stored don't matter. And similarly, from the implementation point of view, the person implementing an interface, implementing a state for a specific model just needs to implement this simple, small operations, relatively simple, like input, it reads state from the disk, or output, or copy. And there's no need to know that this small operation is going to be part of a pretty sophisticated 4D constraint algorithm, maybe. So it's separating this sort of atomic, if you wish, or small operations and how they're implemented from a high-level data simulation algorithm. Another example of a interface class is called increment. So increment is also something in the model space, and it's basically a perturbation to a state. So examples could be an analysis increment here, for example, or just a perturbation to a state. Could be an ensemble perturbation for the ensemble update. So it's a delta perturbation in the state space. The operations that are allowed on increments are wider, or there's a wider range of things you can do with an increment than with a state. You should be able to do some basic linear algebra with the increment to do data simulation. Similarly, for some of the algorithms, you need to be able to evolve the increment forward in time with linear model and backwards with an adjoint, and should be able to compute increment as a difference between the two states. You should be able to have a state at an increment and get another state on the output. So on the observation side of things, there are two classes that are similar in a way to state and increment. The first one is called observations, and this is a vector in the observation space. And examples here, it could be the observation values YO. It could be the result of observation operator or model simulated observation values, H of xb or h of xb plus delta x. So this is a vector in the op space, similarly to how state is vector in the model space. And the operations that are allowed to on observations, or the interface of the observation class, if you wish, allows you to do IO, to copy and assign. And another thing that we should be able to do with the observations, which again is not a part of the observations interface, but it's something, a result of an ops operator, is we should be able to simulate observations given a state. So compute h of xb and have a result of that inside of the observations. The other class in the observation space is called departures. And that's just like state and observations are kind of analogous, but in different spaces. Departures is in that way similar to the increment. So this is a perturbation in the op space. So it could be departures, YO minus HXB. If you do ensemble filters, it could be ensemble perturbations in the observation space. It could be the result of a linear observation operator times increment. And the operations that are allowed on departures, again, are there. You can do slightly more than what you could do with the observations. You could do some basic linear algebra. You should be able to compute departures difference between two observations. Observations here is this class from the previous slide, not the observations values. And we should be able to take the observations, let's say YO or HXB, add departures and get the observations class, object of observation class back. We could compute linear variations in observation equivalent by using linear observation operator. Could also output the result of departures, for example, for the diagnostics. A couple more classes, interface classes, that I'll just briefly mention. There's a class that's called modal, and its linearized counterpart, or the one that's responsible for running linear model or the model adjoint. So this is a class that allows you to propagate state forward in time with a specified time resolution. It could run the model to propagate from T0 to T1. T0 and T1 here are the time resolution that you want to use in data assimilation. Or it could, for example, read states from file with that resolution, or do something else. And then the other relevant classes for the operators are classes that allow you to run the observation operator and its linear and adjoint. There are actually two classes that do that. One is called get values, and that's called first to get those the horizontally interpolated modal values at observations locations. And then after that, the UFO ops operators can take care of the rest of the observation operator. And then there's the linear and adjoint parts for both of those. So you could find more information or see what other interface classes there are in OOPS by going to this directory, oops source oops interface, and basically everything that is in that directory is going to be the interface classes that ultimately need to be implemented to run everything in JEDI. Not all of those have to be implemented, not all of the methods on those classes have to be implemented for a particular application. It depends on the application, what methods are used there. But this gives you the wide overview of everything that needs to be implemented to run everything. And I just wanted to give you kind of a map of what to find where inside OOPS. So there are a few directories inside this OOPS source OOPS directory where the main code is. In the assimilation directory, you'll find main DA classes like minimizers, cost functions, local volume solvers are there, some other helper classes. The base directory holds base classes and classes that kind of build up on interface classes. So you'll find a class like an ensemble of states or an observer that helps you run HFX and the filters and other classes. The generic directory holds some implementations that can be shared by different models and or OBS. So we talked about some generic implementations live in repositories like Yoda and UFO and Sabre, but OOPS also holds a few of the very, very simple implementations that could be shared. And the two examples here are the diagonal ops errors and the pseudomodel. The pseudomodel being the model that just reads states from the files. We talked about what's in the interface directory, and then another important directory is called runs. And that's where all the applications or those top blocks in our diagram, the data assimilation algorithms are, like HFX, variational, etc. I like to just talk a little bit about the HFX application, give you an example of how interface and implementations of those interface classes connect with the OOPS applications through this C++ code. So the HFX application, here's a link to it, runs the model forecast, and it's possible to do it with a pseudomodel by reading states from the files with a specified time resolution, and then computes HFX for the specified observation in a specified time window. This application can also be used to generate observations, for example, for OSSI. So if we look at the HFX application, you'll see it's a pretty short code, and there might be about 50 lines of code if you remove the comments, etc. And here, instead of removing the comments, I just left the comments to show you what it does. So there's this setup section that sets up the observation window, the geometry, which is a class or an interface class that defines the model resolution, MPI distribution, etc. Sets up the model, reads initial states, sets up observations and observer. So observation operators you want to use, and the filters if you want to run any QC filters. And then the bulk of it is running the observer, which is basically running the model and on the fly computing some data to compute HFX and QC filters, and then computing HFX and running the QC filters. There's an option to perturb the result of HFX, which could be used for OSSI, and then HFX can be saved after that. So how does this OOPS application that is written using those abstract classes connected to the concrete implementations of those classes like state and model, etc. So if you look at the main C++ function which is basically the program code, which is in this file, then you'll see it's only 3 or 4 lines long, and the important part there is this line that looks like this. So let's go through the key parts of this. So you see there's an OOPS HFX4D, which indicates which application we're going to run. It's the HFX4D from OOPS. And then after that, there are two parameters in the angle brackets. Angle brackets signify that what's inside them is a template parameter. And there are two of those. In most OOPS application, you'll have two parameters. One is typically called modal, and the other one is typically called obs. So the first one here, FV3 JEDI traits, is for the modal or modal-related interface classes. And the second one is UFO obs traits. This is the obs for the obs-related interface classes. So let's look at what these traits look like. It's a fairly simple, the syntax may look unfamiliar to you, but it's a fairly simple structure that basically sets up, if you wish, a map between what's the class called inside OOPS and what implementation we're going to use for that class. So if you look at this FV3 JEDI traits, this is going to list all the classes that are relevant to the modal part of things. So on the right, there's going to be a bunch of type defs, which is basically type aliases. On the right is the name in OOPS state, the class that we talked about. And then on the left, you'll see the name of the class implementation. So it's a state that's implemented inside FV3 JEDI. So once you pass this structure as a parameter, template parameter to this OOPS HFX for D, the compiler and the linker is going to put in everywhere where OOPS was using state, FV3 JEDI state is going to be used basically. The same for increment and other classes. So that's how this connection at the code level between the implementation of the interface and this OOPS high-level DA algorithm is made. And then the second parameter, the UFO OOPS traits, will list all the classes that are relevant to the observation space things. And since we always, for the realistic models, we always use YODA and UFO implementations, and then all the models are basically going to use this UFO obs traits. So it uses obs space from YODA, obs operator from UFO. So now if I wanted to run HFX4D with a different model, what I would need to do is, well, I'd need to have the implementations of the interface classes for that. So I'd need to have the state and the model and others, etc., implemented for that particular model. And then I'd need to write this 3 or 4 line main program that would have, for example, let's say someone developed an MPass interface, which they actually did. Their main program would look very similar to the FV3 JEDI one, but it would have, so it still has OOPS HFX4D because I want to run that application, but now it has MPass traits instead of FV3 JEDI traits for the model related stuff, and it still uses the UFO ops traits for everything else related. And then if we looked at this MPass traits, then you'd see, again, it would look very similar to FV3 JEDI traits. There would be this type defs for everything that's model related, and then inside on the left side here, I would say which of the classes he uses, state, increment, etc. So that's how that's done at the interface level. And was almost all I wanted to talk about. I also have an example of how HFX application configuration file YAML looks like. So once we've instantiated the application, like on the previous slide, we said with which model we want to run it. When we run the actual executable, we need to pass the configuration file to it. And the configuration file, if you remember, when we looked at the comments in the code for HFX application, there was a whole setup section, and this YAML file basically follows the setup section. So there is a section to set up observation window, the geometry, so the model resolution, the model itself, what the initial where to get the initial condition, the forecast length, because it could be longer, for example, than the observation window, and then all the observations that we want to simulate, where to get them, simulate, sorry, and which observation operators to use.